When people hear the term AI agent, they often imagine an artificial intelligence sitting inside a computer and controlling everything the way a human does. It opens websites, clicks buttons, types messages, downloads files, fills out forms, and maybe even writes code. But what is actually happening behind the screen? How does an AI model, which basically generates text, suddenly gain the ability to operate a real computer? The interesting answer is that most AI agents do not directly control a computer, in the same way our hands control a keyboard and mouse. Instead, they work through a loop. They observe what is happening, decide what action should happen next, execute that action through a tool, and then observe the result again. So in this video, I want to break down that entire process and show you what is really happening when an AI agent uses a computer. Let's start with the most important idea. A large language model by itself cannot click anything. It cannot physically move a mouse. It cannot see your desktop unless something captures the screen and sends that information to the model. It cannot type into a browser unless a separate system gives it permission to send keyboard commands. The language model is mainly the brain of the operation. The eyes, hands, and tools all come from the surrounding software. Imagine asking an AI agent to open a browser, search for a hotel, compare prices, and put the best options into a spreadsheet. The first thing the agent needs is some way to understand your request. The language model reads the instruction and converts it into a goal. The goal might be something like find hotels in a specific city, for specific dates, within a certain budget, and save 3 good options. But that goal is still too broad to execute directly. The agent usually needs to break it into smaller actions. Open the browser, go to a travel website. Enter the city, select the dates. Apply the price filter. Read the available hotels. Compare ratings and prices. Open the spreadsheet. Enter the results. This is often called planning, although the plan is not always created completely in advance. Some agents create a detailed plan before taking action. Others decide only one step at a time, and that brings us to the core operating loop. Observe, think, act, and observe again. The agent first receives information about the current state of the computer. This might be a screenshot, a simplified description of the user interface, the HTML structure of a web page, or data collected through an accessibility system. The model then examines that information and chooses an action. Maybe it decides to click the search field. A control system converts that decision into an actual mouse click. After the click happens, the computer produces a new state. The cursor is now inside the search box. The page might change slightly. The agent receives another screenshot or another description of the interface. Then it decides to type the destination. This cycle continues over and over again. What looks like one smooth task to us may actually involve dozens or even hundreds of individual observation and action cycles. One of the biggest challenges is helping the agent understand what is actually on the screen. Humans can look at a web page and immediately recognize buttons, menus, images, text fields, advertisements, and navigation bars. For an AI agent, this can be much more complicated. There are several different ways agents can understand a user interface. The first method is computer vision. The system takes a screenshot and sends it to a multimodal AI model. The model examines the image and tries to identify important elements. It might recognize a blue button labeled Continue, a text field labeled Email, or a menu icon in the upper right corner. The model can then estimate the coordinates of the element it wants to interact with. For example, it might decide that the Continue button is located around position 820 by 640 on the screen. The automation system moves the cursor to that location and clicks. This method is powerful because it works in a way that is similar to human vision. The agent does not necessarily need access to the internal code of the application. It simply looks at the screen. That means the same general approach can potentially work with websites, desktop programs, remote computers, and older software. But visual control is not always reliable. A button might move because the browser window was resized. A pop-up might cover part of the screen. The page might still be loading. 2 buttons might have similar colors and labels. Even a small mistake in coordinates can cause the agent to click the wrong element. That is why many systems use a second method, structured interface data. On a web page, the agent may be able to read the document object model, usually called the DOM. Instead of looking only at pixels, it can inspect the actual structure of the page. It can see that one element is a button, another is a text input, and another is a link. It may also see labels, element IDs, roles, and accessibility information. So instead of saying, click at coordinate 820 by 640, the agent can say, click the button labeled Continue. That is usually much more reliable. Browser automation tools such as Playwright, Selenium, and Puppeteer work in this general way. They allow software to interact with web page elements directly. An AI agent can use these tools as its hands. The model decides what it wants to do, and the browser automation framework carries out the command. For desktop applications, agents can use accessibility trees, operating system automation APIs, keyboard shortcuts, or robotic process automation tools. An accessibility tree is especially useful because it describes interface elements in a structured form. A screen reader might use this information to understand that a certain element is a checkbox. Another is a menu, and another is an editable text field. An AI agent can use the same structure to navigate an application more accurately. In practice, the best systems often combine multiple methods. They may use structured data when it is available, but fall back to visual understanding when necessary. For example, an agent might use the DOM to locate a search box on a website, but use a screenshot to understand a chart that is rendered as an image. This combination gives the agent both precision and flexibility. Now let's talk about the action side. Once the model decides what to do, it needs a tool that can perform the action. The available actions might include moving the mouse, clicking, double-clicking, scrolling, typing text, pressing keyboard shortcuts, opening applications, reading files, or running commands in a terminal. The agent usually does not generate raw hardware signals. It sends a high-level instruction to an automation layer, something like click element number 12, or type this sentence into the active field, or press Ctrl and L to focus the browser address bar. The automation layer then translates that instruction into an actual operating system event. This separation is important. The AI model handles reasoning and decision-making. The automation software handles precise execution. You can think of the model as a manager giving instructions to a very fast but literal assistant. The assistant will do exactly what it is told, which means the manager needs to be careful. Suppose the AI agent clicks a button and expects a new page to appear. The page might take 3 seconds to load. If the agent immediately sends another click based on the previous screen, it could make a mistake. So computer use systems need timing and verification. After every meaningful action, the agent usually waits for a result. It then checks whether the expected change actually happened. Did the new page load? Did the text appear in the correct field? Did the download begin? Did an error message appear? This verification step is one of the biggest differences between simple automation scripts and more flexible AI agents. A traditional automation script usually follows a fixed sequence. Click here, type this, wait 2 seconds, click there. If the interface changes, the script may fail. An AI agent can look at the new situation and adjust its behavior. Maybe the website displays a cookie banner. The agent can recognize it, close it, and continue. Maybe a button has moved. The agent can search for it again. Maybe a form reports that a required field is missing. The agent can read the error and try to correct it. This ability to adapt is what makes an agent feel intelligent. But it is also where things can go wrong. AI agents can misunderstand what they see. They can choose the wrong action. They can repeat themselves. They can get trapped in loops. For example, an agent might click a button, fail to notice that the click worked, and click it again. If that button submits a payment, the consequences could be serious. This is why responsible computer use systems place limits around what an agent is allowed to do. Some actions may require human approval. The agent might be allowed to search the web and prepare an order, but it cannot complete the purchase without confirmation. It might be allowed to draft an email, but not send it. It might be allowed to edit files inside a temporary workspace, but not delete important files from the main computer. These limits are sometimes called guardrails. They can be implemented through permissions, confirmation screens, isolated environments, tool restrictions, or policy checks. A very common approach is to run the agent inside a sandbox or a virtual machine. Instead of giving the AI full control of your personal computer, the system gives it access to an isolated computer environment. The agent can open programs, download files, and perform tasks inside that environment. But it cannot easily access the rest of your system. If something goes wrong, the virtual machine can be reset. This makes experimentation much safer. Another important part of an AI agent is memory. While operating a computer, the agent needs to remember what it has already done. It may need to remember the user's goal, the steps it completed, the values it found, and any errors it encountered. Some of this information exists inside the model's current context. Other information may be stored externally in a database, a task log, or a temporary working file. Without memory, the agent might repeatedly search for the same information or forget why it opened a certain page. However, giving an agent too much history can also create problems. Long histories cost more to process and may distract the model with irrelevant information. So many agent systems summarize previous actions. Instead of storing every mouse movement, they might store a short record like opened the travel website, entered the destination, selected the dates, and collected 5 hotel results. The agent can use that summary to decide what comes next. Some systems also use reflection. After completing a task, the agent reviews its own work. Did it satisfy the original request? Are the results complete? Did it accidentally skip a step? Should it verify the information one more time? Reflection can improve reliability. Although it does not guarantee correctness, an AI can sometimes confidently approve its own mistake. That is why external checks are still important. For structured tasks, the system may validate the output automatically. If the agent is filling out a spreadsheet, the system can check whether all required columns contain data. If it is writing code, the system can run tests. If it is downloading a file, the system can verify that the file exists and has the expected format. This is where AI agents become much more powerful than simple chatbots. A chatbot mainly gives you information. An agent can use tools to change the state of the world. It can create a file, update a database, send a message, book an appointment, deploy an application, or operate business software. But the moment an AI can take actions, reliability and security become much more important. An incorrect sentence in a chatbot response may be annoying. An incorrect action inside a bank account, production server, or company database could be extremely damaging. So the future of AI agents is not only about making models smarter, it is also about building better permission systems, better recovery mechanisms, and clearer human oversight. I think the most useful way to understand an AI agent is not as a robot magically controlling a computer. It is better to see it as a collection of connected components. The language model is the reasoning engine. The screenshot DOM or accessibility tree provides perception. The mouse, keyboard, browser automation, terminal, and APIs provide actions. Memory keeps track of the task. Verification checks whether the actions worked. Guardrails limit what the agent is allowed to do, and the control loop connects everything together. Observe the computer, choose the next action, execute it. Check the result. Repeat until the goal is complete. That simple loop is behind many of the most impressive AI agent demonstrations we see today. When an agent builds a website, organizes files, researches a topic, or fills out a complicated form, it is usually not performing one giant intelligent action. It is performing a long chain of small actions, constantly looking at the result and deciding what to do next. And honestly, that is also how humans use computers. We look, think, click, check, and adjust. The difference is that AI agents can repeat this process at machine speed, connect to many different tools, and potentially operate for much longer than a human would want to. We are still in the early stages of this technology. Today, agents can be impressive, but they can also be slow, expensive, and unreliable. They often struggle with unexpected pop-ups, changing interfaces, unclear instructions, and tasks that require deep real-world judgment. But as perception improves, tools become more standardized, and verification becomes stronger. Computer-using agents could become a normal part of everyday software. Instead of learning where every button is located, we may simply describe the result we want. The agent will figure out which applications to open, which tools to use, and which sequence of actions can complete the task. The real breakthrough is not that AI has learned how to click a mouse. The breakthrough is that software is beginning to understand goals, observe results, and adjust its own actions. And that is what turns an AI model from something that only talks into something that can actually do work.